Let's have a simple and practical video on the theory of finite element method. I strongly believe that engineers need to learn basic theory of finite element method if they want to make more reliable and also more computationally efficient finite element models. Hi, I'm Dr. Iman. Welcome to Academy. One of the good ways to go into the theory of finite element is to create an analogy with numerical integration. In fact, different things that we do in numerical integration can help us understand the theory of finite element better. What do we do in integration? If we want to find the integral of function f of x from point A to point B, there are two ways. One way is to do this by analytical method. However, the problem with the analytical method is that it requires that we have a simple function to integrate. If the function is not easy to integrate, then we can use the numerical integration. One way to do the numerical integration is to divide the area under the curve into smaller pieces. Here, I am doing this by dividing the whole area under the curve into 9 areas. And then I can just add them up to find an estimate to this integral. As you can see, these smaller pieces cannot cover the entire area under the curve, but still they can give us a good estimate. If we want to have a better accuracy or better estimation, one thing we can do is to increase the number of divisions. Here on the left we have 9 divisions, and on the right we have the 18 divisions. You can see that now with 18 divisions we have a better accuracy or better estimation of this integral. So I2 is bigger than I1. This is very similar to what we do in finite element. In fact, many of you are possibly already familiar with the mesh convergence in finite element. We can start with a coarse mesh, and then if we want to increase the accuracy, we go into a fine mesh. But we cannot continue dividing the area under the curve into smaller pieces. Just in an extreme, like you cannot have like infinite number of pieces, because then you cannot add infinite number of areas. This is computationally not possible. So this is the same thing in finite element. In finite element, you can discretize the model into smaller pieces or a smaller element, but there is a limit. We cannot continue doing this forever. However, with small enough elements, we can actually get a really good accuracy in our model. One thing that is important in finite element method is the definition of the field variable. Another name for the field variable is degree of freedom, and another name is nodal variable or nodal values. The field variable has a very simple definition. First, we need to define field. Field is any space where a variable can change. For example, in structural mechanics, displacement is the field variable as it changes from one point to another point in the model. For example, here on the left, we have the total displacement at this point as 200ths of a millimeter, and on this point 7,000ths of a millimeter. So you can see that the displacement is changing from one point to another point. And the field is in fact the space or the structure that we have, something that you can touch, something that you can deform, something that you can apply load. This is the definition of the field. Another example for the field is when you want to do thermal analysis. In thermal analysis, the field variable is the temperature instead of displacement. For example, on the right, we see that the temperature at this point is 6.5 Kelvin and the temperature at the other point is 3.8 Kelvin. So you can see that the field variable is changing from one point to another point in the field. So it's very important that we know the definition of the field variable or degree of freedom. Degree of freedom is a possibly a more familiar name. So from dynamics, you might be more familiar with degree of freedom. However, the degree of freedom in finite element has a little different definition, and we're going to talk about that. Consider that you have a physical model where you have uniform loading on it, and also the left side of it is fixed. So these are all called boundary conditions. There are two different types of boundary conditions. One is called essential boundary condition, and the other one is called natural boundary condition. In theory of finite element, the essential boundary condition is when we fix the field variable itself, here being the displacement, and the natural boundary condition is when we set the first derivative of the field variable equal to a number. These are for example, uniform loading and traction-free surface like this. Another name for natural boundary conditions as engineers use is just loading. If this physical model is simple to solve, we can just do it analytically, and we can just find a closed form. That's when we are lucky, right? If we can actually find a closed form for this problem, that's great. If the geometry is complicated, or the loading or the boundary conditions are complicated, we cannot solve this analytically. So what do? We need to solve this numerically. When we want to solve this numerically, like what we did in numerical integration, we need to divide this whole area into smaller pieces. In fact, like integration, we cannot have infinite number of areas. So having infinite number of areas for numerical integration is equivalent to having infinite number of points inside this physical model. In fact, this physical model is a continuum, right? So it has infinite number of points. If you want to solve this numerically, you cannot do that with infinite number of points. Then what do? We divide the entire area into a smaller elements. And then we can actually now make a new model that we call finite element model. In finite element model, as you saw, we divide the entire area into a smaller pieces that we call element. These elements are going to share some edges, and also they're going to share some corners or some vertices. So these corners or vertices are called nodes. Because this new model, that is a finite element model, has only nodes and elements, we apply the load only on the nodes, and we apply the boundary conditions only on the nodes. We cannot really apply them anywhere else. That is our finite element model. After having this very quick introduction to the finite element method and how we can use the integration analogy to understand it better, now let's look at behind the curtain in the theory of finite element to see when you hit solve in software like ANSYS Workbench or Abacus or Console, what happens behind the curtain. Here we want to only focus on very specific type of theory of finite element, which is called direct stiffness method. This is the simplest type of finite element method, though while very simple, we can actually use this method to understand the basics of finite element method. Let's see what is behind the curtain. The first thing I want to mention here is that finite element analysis or finite element method happens at the intersection of two words, physics and math. We're going to use the both words, math and physics, to prepare our finite element theory or our finite element model. This is very important. We use math as a tool, but we always need to remember that we need physics to understand FEA. Math without physics in FEA doesn't work. That's very important. To explain the basic theory of finite elements, I have created 8 steps. So one by one, we're going to take these steps so that we can learn the basics of the FEA. Hopefully, we will enjoy this journey together. Okay, first step is to select the element type and discretize the model. Consider that you have a system of springs as shown here. If you take one spring out, then you will be able to create a physical model for that spring. So it has a spring constant, and you can have a stretching force on it, and the force would create a displacement delta. Force and displacement delta are going to be related to each other using the Hooke's law. In dynamics or statics, this spring has only 1 degree of freedom, which is just motion in x direction. We want to create the finite element version of this model. So this is the finite element version of this spring. It has 2 nodes, node I and node J, and each node has 1 degree of freedom, ui and uj. And also each node has one internal force that is being applied to the node, fi and fj. For this model, by convention, we show fi and fj both in positive direction. This finite element has also a stiffness that is shown as ke. Very important fact about this element is that it has 2 degrees of freedom, so not 1 degree of freedom. This is a big difference between the physical model and the finite element model. In the finite element model, each node has its own degree of freedom. You can actually move them independent from each other. So because of that, this element by itself has 2 degrees of freedom. Ui and uj is not x, y, or z. It is ui and uj. One important step in any finite element modeling is to discretize the model. However, when you have a system of springs, the model is already been discretized. You already know these springs are your element 1, element 2, element 3. But in many other cases, when you have, for example, a solid geometry, you need to spend some time discretizing your model into smaller pieces. For example, if you have this model, after discretization you see the mesh on the model. Okay, remember, here we are doing the simplest possible theory of finite element. We can make this very complicated very quickly, but that's not my intention. I just want to make it as simple, but at the same time as practical as possible. Okay, now let's go to step 2. In step 2, we select an approximate function. What is this approximate function? Just imagine that you have this spring again, and then this spring is fixed on the left end and the right end is under the load F. This spring has the length of L and the x direction is shown here. If I apply this F, a good question to ask is that how can I find the displacement at any point along the spring? Hopefully, one guess that you will also come up with is very simple linear case. U is equal to a1 plus a2x. You can see that here now I have 2 coefficients. How can I find those coefficients? I can just use the boundary conditions on this element to find those coefficients. What are the boundary conditions on the elements? I know that node 1 on the left has the degree of freedom u1, and node 2 on the right has the degree of freedom of u2. So these are the boundary conditions. If I plug these boundary conditions in u, then I will be able to find a1 and a2. Let's do it. U at x equal to 0 is a1. If you set x equal to 0 here, u is equal to a1. And also from this element, you know that u is equal to u1 for 0.1. The other one is that u at x equal to L. If you set x equal to L here, you get a1 plus a2L. And then also at x equal to L, u is equal to u2. So now you can find a2. Now if you substitute a1 and a2 back into your equation for u, you will get this equation. U equal to 1 minus x over L u1 plus x over L u2. One thing that engineers want to do in finite element method is to write everything as a matrix form, and we want to do the same. In a matrix form, I can write u of x, because u is a function of x, is 1 minus x over L. X over L, this is a 1 by 2 matrix, times u1, u2. You can see that the multiplication of these 2 matrices is going to create the same thing that you see here. I can name 1 minus x over L as n1 and x over L as n2. This matrix, matrix N, that by itself has 2 elements in it, is called matrix of shape functions. It's a very, very important matrix, and we will be using this a lot in finite element method. Now I can just rewrite everything in a simple form, and this is going to be my final equation. So ux is equal to na, n1 is 1 minus x over L, and n2 is x over L. You can see that it is extremely simple. Now we are at this point. I want just to spend some time on telling you how important this u equal to na is. So u equal to na is doing approximating for you. So what it does is that if I know u1 and u2, that are the nodal values or the degree of freedoms for node 1 and node 2, how can I find the displacement of any other point in this element using u1 and u2? This is what this equation does. For example, if the point is in the middle, then x is equal to L over 2. So then n1 and n2 are going to be both 0.5. And then that will estimate or approximate u at the midpoint. In fact, this is the formula that creates those colorful counterplots in finite element that we like to put in our report. This equation is extremely simple and extremely powerful. So I want you to really appreciate how important this formula is, and that's why I'm spending more time on this. You can also do many more advanced stuff in finite element. For example, if you want to do submodeling, if you want to do remeshing, these all come from this very important formula. So don't forget that u equal to NA. Let's go to the next step. The next step is to find the element stiffness matrix for each element that we have in our structure. Like numerical integration, to find the area under the curve, we need to find the area of each rectangle. That is the equivalent to this step. Now we have this element that is shown on the left that is equivalent to the physical model on the right. I want to find the stiffness matrix for this element. As I told you before, in physical model, I have a stiffness constant or a spring constant, which is actually a scalar. However, on the left, I have the finite element, and this finite element also has a stiffness, but it's not just a scalar. We will show that the stiffness of this element is not a scalar, and it is in fact a matrix. Let's get to it. To derive the stiffness matrix for this element, we need the left and the right side. We need the physical model and the finite element model. We're going to be using both of them. F1 is equal to negative t. Just by comparing the left and the right, you can see that F1 is equal to negative t because they are in opposite directions, and F2 is equal to t. T is equal to k u2 minus u1. And what is u2 minus u1? u2 minus u1 is the delta. If u2 is bigger than u1, it means that the spring is under tension. If u2 is smaller than u1, then T is going to be compressive force. T is equal to k u2 minus u1, and from here we can see that it is equal to negative F1. Also, T is equal to K, U2 minus U1 again, but it is now equal to F2. If we rearrange these formula, we will get these new ones. F1 is equal to K, U1 minus U2, F2 is equal to K, U2 minus U1. As I told you before, we want to write everything in finite element in a matrix form. So in a matrix form, these two equations are shown as this one. So as you can see that if you multiply this matrix to u1 and u2, you will get these two equations. This is also very important thing. So in fact, now you can just rewrite this as in a more generalized form, and F is equal to KEA. KE is the stiffness matrix that is shown here. K minus K minus K, K. That's called a stiffness matrix. And this formula is also extremely important in finite element method. It is called characteristic formula. Characteristic formula in finite element method relates the force to the field variables. Because this is also extremely important, I want to spend more time on this, okay? So again, reconsider this finite element that you see here and the characteristic formula. In the characteristic formula, F is called nodal force vector, KE is the element stiffness matrix, and A is the vector of element nodal field variables like U1 and U2. And KE now is shown here as K, negative K, negative K, K. This matrix is associated with 2 degrees of freedom, U1 and U2. That's extremely important. We will be using this in the next slides. And this matrix, by the way, is 2 by 2. It is very important that you understand how we can possibly guess the size of the stiffness matrix, knowing how many degrees of freedom one element has. The formula is this. Here we have 2 by 2 because we have 2 nodes and each node has 1 degree of freedom, and because of that in total we have 2 degrees of freedom, and then we have 2 by 2. Remember that the stiffness matrix for an element has to be always a square matrix, so it's 2 by 2, n by n. I promise you that I'm not going to make this very complicated, but I think now we are at a point that I can show you a little bit more than one-dimensional element. Consider this 2-dimensional triangular element that has 3 nodes. It's actually in a plane, it's a triangle, and it has 3 nodes, and each node now, instead of 1 degree of freedom, has actually 2 degrees of freedom, u and v. You can see that this is ui vi, uj vj, and uk vk. How many degrees of freedom in total do we have? We have 3 nodes, each node has 2 degrees of freedom, so in total we have 6 degrees of freedom. Now I'm going to ask you, what is the size of the stiffness matrix? I'm going to give you 2 seconds. Ready? Hopefully you could guess. It is 6 by 6 because you have in total 6 degrees of freedom. Let's go to the next level. The next level is when we have a 3-dimensional element. This is the tetrahedral element that has 4 nodes, and each node now has 3 degrees of freedom, u, v, and w. U is the displacement in x, v is the displacement in y, and w is the displacement in z. How many total degrees of freedom do we have for this element? Hopefully you guess 12, and here then the stiffness matrix is 12 by 12. This is actually how we know the size of the stiffness matrix. This is step 3 where we derive the element stiffness matrix. Now let's go to step 4. In step 4 we want to derive the total stiffness matrix. So in step 3 we derive the stiffness matrix for a single element, but now we want to do this for all the elements and for the entire structure. This is equivalent to finding the total area under the curve when we do numerical integration. To do this, I want to have a very simple structure. So this structure has only 2 springs. This is enough for our discussion, because if you have just bigger structures, the calculations are just going to be more, but the concept is still the same. So in this structure, we have 2 springs that we show as element 1 and element 2. The spring constant for element 1 is K1 and it is K2 for element 2. The node numbers are shown as 1, 2, 3. You can choose different pattern of node numbers. Okay, it will have some effect, but not really a big effect for a smaller models. As you see here, we have the stiffness matrix for element 1 shown as K1, K superscript 1, which is K1, negative K1, negative K1, K1. It is 2 by 2 matrix, and then also we are showing the stiffness matrix for element 2. I want to ask you a question. If I have the element stiffness matrix as 2 by 2 matrix, what would be the size of the stiffness matrix for the total structure? If we use the same method that we use to find the size of the stiffness matrix for a single element, what should we do? If you want to use the same method, we will see this. So we have 3 degrees of freedom total. So then the stiffness matrix is going to be 3 by 3. We have 3 nodes. Each node has 1 degree of freedom. So then the total degree of freedom is going to be 3 by 3. It turns out that this is actually the right method. We can do this also by just writing all the force equilibrium for each one of the springs, and then for the entire system, and we find it. But I'm not going to do that, so I'm just going to go ahead with this method. As I told you, step 4 is equivalent to what we do in numerical integration. In numerical integration, we find the area of each piece and then we add them up. Can we do the same thing here? Now that we have the stiffness matrix for each element, can we just add them up and get the total stiffness matrix? I hope you are seeing the problem. As you can see here, this is not really possible. because you have two 2x2 matrices, K1 and K2, and the resultant K total should be 3x3. How can we add 2x2 matrices and get a 3x3 matrix? How can we do that? To do this, I'm gonna go into again the intersection of physics and math. As I told you before, FEA happens at the intersection of the physics and math. Let's take a look at the characteristic formula for each element. Here on top, we have the characteristic formula for element 1. You have F1 and F3 because F1 and F3 are attached to element 1. This is the stiffness matrix for element 1. And then we have 2 degrees of freedom, U1 and U3. For element 2 also, we have U2 and U3. So these are the degrees of freedom associated with element 1, U1 and U3. And these are the degrees of freedom associated with element 2, U2 and U3. This is where physics come to prevent us from doing something wrong. And this is what can go wrong. Here, while mathematics allow you to add K1 and K2, because both of them are 2x2, physics doesn't allow you to do that because K1 is associated with U1 and U3 and K2 is associated with U2 and U3. You can see that they are associated with different degrees of freedom. So while mathematics can allow you to add them up, physics won't allow you to do that because they don't have the same nature. So mathematics will say you're good to go. Physics will tell you no, you can't, because they are physically not equivalent. Because of that, you cannot add them up. So then the question is that how do we go from two 2x2 matrices to a 3x3 matrix? To do this, let's go to the next slide. We are still on step 4, but now I want to show you how I can add K1 and K2 to find the total stiffness matrix. It turns out that we can fix this issue using a very simple method. We just find which degree of freedom is missing, and then we add that degree of freedom to the stiffness matrix, but with a little bit of trick. So this is a new matrix that we have made. It's called expanded stiffness matrix for element 1. For element 1, which degree of freedom is missing? You can see that the missing degree of freedom is U2. So what we do, we add 1 columns of zeros and 1 rows of zeros for the associated degree of freedom. And because U2 is the second degree of freedom, then we will add that column of zeros and that rows of zeros as the second column and the second row. We can do this for element number 2. The missing degree of freedom is U1, so we add 1 column of zeros as the first column, and also we add 1 row of zeros as the first row. And these are now associated with all the degrees of freedom. You can see that for the missing degree of freedom, we add 1 column of zeros and also 1 row of zeros. This is actually how we fix this issue. Now you can see that each one of these expanded stiffness matrix is a 3x3 matrix, and they both have all the degrees of freedom. So physically they are equivalent. That's very important. Another thing that matters here is that really this K1 on the left and K1 expanded and also K2 and K2 expanded are physically the same, while mathematically they are not the same because one of them is 2x2, the other one is 3x3. Physics allow us to do that, but not mathematics. Remember that finite element is at the intersection of 2 words, right? Mathematics and physics. That's the important thing here. Then now you can see that K total can be calculated by adding K1 expanded and K2 expanded. Both of them are 3x3 and they are okay to be added both mathematically and physically. And all the degrees of freedoms now are in the stiffness matrix. And this is again called total stiffness matrix. So in total stiffness matrix, we need to have all the degrees of freedom. For example, if you have a structure with 100 nodes and also each node having 1 degree of freedom, then the size of the total stiffness matrix is going to be 100 by 100 because you have 100 total degrees of freedom. Now that we have K total, we should take a look at some of the characteristics of this stiffness matrix. If you take a look at this matrix, you can see that it's symmetric. That's one of the main characteristics of the stiffness matrices. In many cases, in the structure, especially in the structural mechanics, the stiffness matrices of structures are symmetric. The other fact about a stiffness matrix is that the diagonal terms cannot be negative. Again, physics doesn't allow it. One other important thing in here is that if you take a look at the diagonal terms, you can see that for U1 we have K1, for U2 we have K2, but for U3 we have K1 and K2. The reason that we have the summation of K1 and K2 is that node 3 is shared between the two elements. That's very, very important thing. This is the principle of the continuity of the deformation or displacement from one element to another element at their shared node. Because I want to keep this as simple as possible, I don't go into the details of this, but I just want to tell you that these exist and these are important items. For non-believers, I think it's good to show you another step just to make sure that creating an expanded stiffness matrix is not the wrong thing to do. It is actually physically correct. Okay, take a look at this slide. Here, again, we are still on step 4. But I'm showing you this slide because I want to use another verification layer to show that what we did in the previous slide, where we found the expanded stiffness matrix, was actually a good thing to do, physically correct thing to do. So if you write the characteristic formula for each element, but now with all the degrees of freedom, so you see something like this for element 1, and this is for element 2. So element 1 will give you F2 equal to 0, and element 2 will give you F1 equal to 0. Element 1 doesn't have node 2, so F2 is equal to 0. Physically, F2 doesn't exist for element 1. The only internal forces on element 1 are F1 and F3. And the only internal forces for element 2 are F2 and F3. Again, for element 2, F1 doesn't exist. This is another layer of verification. Now that we have found the total stiffness matrix, we're going to go to the next step. In the next step, we are going to just write the characteristic formula for the entire system of a spring or the entire structure. So you can see that this is pretty simple. You have F1, F2, F3 on the left hand side, and then you have K total times U1, U2, U3. You can also write it in a more compact form. F is equal to K total A. And to solve this problem, you will do this way. So A equal to K inverse times F. But can we do it? We're going to discuss that. This step is pretty straightforward, and we're going to go to the next step. Let's go to step 6. In step 6, we want to apply the external forces and solve the characteristic formula. The only force that is being applied on our spring is F2. So F1 and F3 are 0. And then we have this formula, F is equal to K total A. To find A, we can find the inverse of K total and multiply that by F. So it turns out that we cannot really solve this equation. Why? Because this structure doesn't have any constraint. In fact, if we have this structure and we apply an external load to it, it will have a rigid body motion. The whole structure will accelerate, right? Because there is nothing in space to prevent that. This rigid body motion means that U1, U2, and U3 are going to be all equal. We will have equal amount of displacement on all the nodes, and they will have infinite number of answers because at any time they could be anywhere in the space. This is an issue. We have infinite number of solutions, and this is not good. In finite element, we want to have just one solution. We cannot report infinite number of solutions. We are not doing a dynamic analysis. This is not a rigid body motion. This is a displacement, a deformation. In deformation, you need to have a constraint. So this is not possible to solve. Then we need to change step 6. We need to edit this step. Instead of apply the external force and solve the characteristic formula, we need to apply the boundary conditions and external forces. Then we will have something like this. We will have a system of a spring that is under a load and it is actually constrained on the left side. In physics, what's going to happen to this structure? This structure is going to be stretched. You can see that node 1 is always fixed. It's not going to move. Node 2 is going to have the highest amount of displacement, and node 3 is in the middle. So they are not equal. We have already applied the external forces on the characteristics formula. Now I want to apply the boundary condition. The only boundary condition I have here, which is actually essential boundary condition. Again, as I told you before, there are two types of boundary conditions, essential and natural. Essential boundary condition is when we apply the boundary condition on the field variable itself. The field variable is u1. u1 is equal to 0. How can we apply the boundary condition to our characteristic formula? We have already edited the left hand side. Now we want to do something on the right hand side. If u1 equal to 0 is considered as one equation, how can we change this matrix so that it can recreate this equation? It turns out that it's a very easy way to do it. In fact, if we change the diagonal element into 1 and other elements in the first row to 0, the first line will be 1 times u1 plus 0 times u2 plus 0 times u3 equal to 0. This is u1 equal to 0. And we also change all the elements in the first column because we always want to keep the stiffness matrix, no matter what we do on it, symmetric. And in fact, we need to keep it symmetric because u1 is still 0. So we don't want to multiply k1 to u1. So if u1 is 0, we can just write k1 is 0, right? It doesn't really change anything physically. This is how we edit the stiffness matrix so that we know it resolves into a definite answer. In this problem, then, we have a new matrix. The changed matrix, the stiffness matrix, the total stiffness matrix has been changed. Now we call it total stiffness matrix with superscript BC, meaning that boundary condition has been applied to it. We now have a new equation, F is equal to K total BC times A. We can solve this equation. So if you take a look at the two versions of the stiffness matrix, you can see that initially we had K total. The determinant of K total is actually 0. And that's another reason that in the previous slide, we had the issue with infinite solutions, because the determinant of K total is 0. When the determinant of K total is 0, we cannot invert it. To be able to invert a square matrix, it needs to have a non-zero determinant. This is coming from matrix algebra. Now, when we apply the boundary condition, we get to a new matrix, which is K total BC. And if we calculate the determinant of this new matrix, we will see that it is not equal to 0. And that's why now we can solve this problem and it will give us the right answers. Now we're going to go to step 7. In step 7, we solve the characteristic formula that now has been edited by applying the boundary conditions and also by applying the external forces. This is the new equation. As you can see, F is equal to K total BCA and A is equal to inverse of the new stiffness matrix times F. Okay, if you solve this equation, you will get u1 equal to 0, u2 and u3 are also given. u1 equal to 0 is coming directly from the boundary condition. We didn't have to really calculate it, but it is still there. Now that you have all the answers, one of the most important steps actually in finite element is really verification of the result. I didn't include this as an actual step in the theory, but in many cases, when you do a finite element model, you need to verify your results. You need to validate your results. results. Okay, there is a slight difference between validation and verification. Hopefully I will explain this in future videos. So the next video I want to make is about practical considerations and tips on performing a good finite element analysis. So we will be talking about the difference between validation and verification in that video. But it's still good just to check whether these formulas and these results make sense. One of the things that we can do, for example, to see is that if you actually you have this answer, you can actually compare with theoretical analysis. For this very simple model, we have the analytical answer. We can actually use that. And as you can see, it turns out that these results are correct. The other validation we can do is that both U2 and U3 are actually bigger than 0. And that's another validation. Sometimes we want to make sure that the deformation that we expect, that it should be negative, it is actually negative. A deformation that is expected to be positive, it is actually positive. So these are different layers of validation we do on our results. Now that we have the results and we have validated them, hopefully we can be happy and we can go to the next step. But before we go to the next step, I just want to open a small parenthesis here and talk a little bit about the inverse of the stiffness matrix. Remember that in this small problem, we only had like 2 springs. So the stiffness matrix was like 3 by 3. However, in complicated models, we might actually have 1 million degrees of freedom. Then the total stiffness matrix will be 1 million by 1 million. It turns out that finding the inverse of this stiffness matrix is extremely inefficient and computationally expensive. So commercial software like ANSYS and Abacus and COMSOL or other commercial software like Altair use other types of solvers. So one of them is called direct solver. They use LU decomposition to solve a system of algebraic equations. You can see that this characteristic formula is actually a system of algebraic equations. And the other way is using iterative solvers. Okay, if you're dealing with a very, very big model, then iterative solvers are good ways to do this. So the iterative solvers, we definitely need to start with an initial guess, and step by step we correct it until we get to the answer. So it turns out that these methods, these kind of solvers, are more efficient than finding the inverse of the stiffness matrix. While in the theory we talk about finding the inverse, but in practice they don't find the inverse of a very big stiffness matrix. They use direct solvers or iterative solvers. Now that we talked about this, let's go to step 7. So in step 7, we're going to do post-processing. See, everything is now with green check mark. We have U1 and U2. We have, in fact, all the degrees of freedom. Like for the system of a spring that we had before, we have U1, U2, U3. Now the question is that now that we have these degrees of freedom, how can I find some other outputs? This could be, for example, nodal strains, it could be stresses, it could be reaction forces, contact pressure, strain energy, thermal gradient. If you're doing a thermal problem, you are interested in thermal gradient, you're interested in heat flux. How can we do that? The good news is that now you can actually solve or find all of these very quickly. In fact, majority of the runtime in finite element is dedicated to solving that characteristic formula, like 95% or even more than that. After you find all the degrees of freedom, the rest is extremely simple. Do you know how do we do that? We are gonna use a very, very, very important formula. Hopefully you remember what formula I'm talking about. So we need to go back to step 2. Hopefully you remember. In step 2, we had a very important formula, U equal to NA. This is our best friend here. Our best friend is going to help us find all those outputs using the known U1 and U2. I'm going to show you one example, but you can actually use almost the same concept to find some other outputs. We're going to also use, as I told you before, we actually have 2 good friends. One is U equal to NA, the other one is F is equal to KA. Let's just use one of our best friend to calculate the strain on an element. So to find the strain, we're just going to use U equal to NA and n is 1 minus x over L and x over L. We know from the theory of elasticity that epsilon x is du over dx. And if you take the derivative of u with respect to x, you get this matrix multiplied by this matrix, and then if you multiply them, you get u2 minus u1 over L, and u2 minus u1 is delta. This is actually the familiar formula for a strain, right? A strain is delta over L, but I wanted to show you this way so that you know how we use u equal to NA in finite element. Now that we have a strain, we can also find a stress, right? That's actually how we find a stress and a strain in finite element. Another output that we are interested in is the reaction force. Remember, we are still in step 8 where we do all the post-processing. Another output is the reaction force. If I have this spring, how can I find the reaction force? It turns out that to find the reaction force, we need to use the original characteristic formula. You remember that we changed the characteristic formula by applying the external forces and the boundary conditions into this form, K total BC. But now if we want to find R, which are the reaction forces, we need to go back to original characteristic formula where we see K total times A. To do that, let's just have K total as written before, and then 0, U2, U3. 0 is just U1 and U2 and U3. You have U2 and U3, we calculated those, and if we multiply these two, we will find the total external forces being applied to our structure. On node 1, I will have R1, which is the reaction force on node 1, and then node 2 has F2, and node 3 doesn't have any external forces, so it's 0. So you can see that if you do this calculation, you will find that R1 is equal to negative F2. And again, this is another validation point that we compare the external forces to the reaction forces in our structure. Even in the most complicated models, finding the reaction force and making sure that the reaction forces on the boundaries are going to balance the external forces that are being applied to the structure is actually one of the validation method that many engineers use for these models. It turns out that when you want to apply the external forces in finite element, reaction forces are not considered as external forces. You remember that at step 6, we actually applied the external forces and also boundary conditions, but for external forces in here for node 1, we didn't put R1, we actually just put 0. It is 0 because the first line will give us 0, right? We cannot put R1 here because then the first line will give you 1 times U1, and U1 is already 0, so you cannot have R1 here. When you apply the external forces and the boundary conditions, you don't consider reaction forces as external forces, and then you can calculate them later when you have the answer to the problem. Okay, with this, I'm done with these 8 steps that show you the theory of finite element. Again, the basic theory, which was the direct stiffness method. Before we go into the summary of all these steps, I want to do a very quick comparison between what we do in a static or mechanics of material and FEA. Suppose that you have this structure like a truss and then you apply load to it, okay? Again, let's just keep it very simple. In a static or mechanics of material, hopefully you remember what we do. We find F from like method of section or other methods, method of joints, method of section. We find F on member 1, 2. From F, we find sigma because we know the cross-sectional area of that member. And then from sigma, using Hooke's law, we can find epsilon. And from epsilon, knowing the initial length of that member, we can find delta. This is how we find the deformation on that member. It is very interesting to compare this to FEA. In FEA, we do exact opposite to this. In FEA, the most fundamental thing when you solve an FEA problem is delta. From delta, you find epsilon, knowing L. From epsilon, you find sigma using Hooke's law. And from sigma, you will find force, knowing the cross-sectional area. See, this is exact opposite to what we do in a static or mechanics of material. The most beautiful thing about FEA is that it doesn't care if you have statically indeterminate or determinate systems. It can do any system, no matter how much boundary conditions you have on it. Hopefully you remember when we had the issue of statically indeterminate systems in statics, we used the displacement equation from mechanics of material to add more equation to our problem so that we could solve it. But in finite element, the displacement equations are actually the foundation of the solution. We start from the displacement and then we find others. And that's why in FEA, we don't care if our problem is statically determinate or indeterminate. It can actually solve both. With this, let's go to our summary. In FEA, we have 8 key steps in theory. In the first step, we select the element type and also discretize the entire model. When we know the element type, we know how many nodes we have and also how many degrees of freedom per node we have. The spring element is the simplest element. You can have triangular element, you can have tetrahedral element, you can have hexahedral elements, right? There are different types of elements. You can have shell elements, okay? So many different types of elements, and each one of them comes with their own nodes, their own degrees of freedom, their own stiffness matrix, their own shape functions, right? So, but the concept is the same. For step 2, we select the shape function or that approximate function that we want to approximate the displacement or the field variable at any point other than the nodes to actually create a colorful result. Now let's go to step 3. For step 3, we find the stiffness matrix for a single element. In step 4, we find the total stiffness matrix for the whole structure. In step 5, we write the characteristic formula. This is a very small step, but I want to keep it in there because I want to tell you that we cannot solve this equation because the determinant of K total is actually 0. How do we make the determinant non-zero? By applying the boundary conditions. We also apply the external loads, and then we can actually solve the new characteristic formula. You can see that now instead of K total, we have K total with BC applied to it. And the determinant of K total BC is not equal to 0. We can solve it and we will get a definite answer. One answer, not infinite number of answers. And in step 8, we post-process to find many other outputs like support reaction, strain, stress, heat flux, contact pressure, many other things that we can actually find. So these are the key steps in a very basic and simple finite element theory. As I told you, we only talked about the direct stiffness method. There are other methods in finite element. For example, the variational method, the minimum potential energy method, the Galerkin method. The result of all of these methods is the stiffness matrix. The stiffness matrix is one of the most important thing in finite element. When we have the stiffness matrix, it's a big thing in finite element model. The next thing is just to solve the characteristic formula. But before solving the characteristic formula, we need to apply the boundary conditions and we also need to apply the external forces. But finding K total is the main goal of different methods in finite element. I want to just have one more slide to show you, and this is extremely important. I want you to take the message on the next slide with you after you're done with this video, and this is this. The most important formula in finite element. One is F is equal to K total A, the characteristic formula, and the next one is U equal to NA. So these two are extremely important, and that's why I'm telling you, if you are an engineer who wants to run a reliable and computationally efficient finite element model, you need to be familiar with these two. They will give you a lot of more insights about the finite element simulation. Again, in the next video that I will make about practical tips in finite element, I will show you how we use these to understand, for example, the stress singularity, how to deal with the stress singularity. Is force also singular in finite element, or is it just a stress that is singular? So we will talk about this, okay? More advanced stuff, I promise you that. With this, I'm done with this video. I hope you enjoyed it, and hopefully our next video comes soon. I wish you all the best, and have a good day. Bye.